We previously derived the solution for the homogeneous second order or source-free second order system response where the system is critically damped, that is, it has a damping ratio identically equal to 1, and real and repeated eigenvalues, or real and repeated roots to the characteristic equation. And we found that the homogeneous solution takes on this form right here. Right? So the question is, what does that mean? How does a critically damped second order system behave? Well, a critically damped second order system is the borderline between an overdamped system and an underdamped system. And an underdamped system exhibits oscillations, whereas an overdamped system approaches steady state without any oscillations. So the critically damped case is the case where we start at some non-zero initial condition and we approach steady state as quickly as possible without overshooting the final condition. So that means if we think about our mass spring damper system with the block that was sliding, in this case, the system is such that when we let go of the block, it's going to start at its initial position and it's going to quickly slide back towards its equilibrium position, and it's going to reach there, but it's not going to bounce back and forth. So it's going to start at one spot, slide very quickly back to its original position, and then not move from that position, from that resting position. So here, in this case, we don't see any oscillations because it doesn't go past its equilibrium position. It doesn't go to a position of some value of negative position. Of course, our derivative initial conditions are going to impact this response, but we still see that even if we have an initial velocity or an initial condition in the negative direction, we still don't overshoot the steady state. We still approach the zero value and we never go below zero in this case. Okay, so a critically damped system is like an overdamped system. It's just the fastest responding overdamped system before we get into a underdamped system where we're going to see oscillations.